So let me summarize a little bit what we saw last time, and emphasize how general the phenomena is, and give it a few names that last time I did not mention. So yesterday we started thinking that our table, when we have our lattice, could have some continuous symmetry rather than just up or down, which is a symmetry. You flip x to minus x, it was a symmetry. That was the Z2 symmetry. It could be, say, some ON symmetry, where at each point I have a vector that can point in any continuous direction. And this is a symmetry in the sense that my action at x, at the field x, is equal to my action at the field d dot x, where d is an ON rotation. So that's what it means to be a symmetry. So x transforms in the vector representation of ON, and we wrote some simple action for it, which was here. And this potential here could have a minimum if this m squared was positive, or a line of minima if m squared was negative. Now let me emphasize that this is a line in quotation marks. It's a line when we can draw it, but in fact it's an n-1 dimensional space. Because if we have n components, you have to generalize this picture, and there are n-1 dimensions here. Right? So how do we think of these n-1 dimensions here? They are just how many directions I have perpendicular to this arrow here. Right? So here we fix the vacuum to be 1, 0, 0, 0, 0, and there are n-1 zeros there. Right? So those are these n-1 dimensional directions that cost no energy to move. Okay. Now let me emphasize also that in the continuous limit, where we can think of smooth configurations, x at the lattice point n becomes a function x that depends on some smooth variable n, and that's what we call a field. And this n then becomes some smooth coordinate transformation. And rather than doing a usual integral over each x1, x2, x3 up to xl square, we use this fancy notation to indicate we do a path integral with sum over all possible field configurations. And if we don't know exactly what this means, we just discretize and go back here where everything was well defined. Right? So this is defined as a limit of this. And then my action, the normalization is such that this lattice term becomes just 1/2 times the derivative of the field square, because this is just a derivative. And the fact that the 1/4 goes to a 1/2, it's because each link appears twice. There is n with n plus 1, and when you go with n plus 1, there's n plus 1 with n minus 1. So each link appears twice, so that's why it becomes nicely normalized now. And then I just copy-pasted this, and that's the potential v of x. That could be this or this. Then in the tutorial, let me just remind you and redo it in a bit more graphical way perhaps than what you did in the tutorial, and I just want to introduce this notation. You expanded around this minima. We did it in class with one parameterization. We said if the solution is roughly at that minima, which I know the absolute value but not the direction, so we parameterize the vector with some absolute value but unknown direction. But another way we could have expanded is more straightforwardly. We just write field equal to classical field plus fluctuations and plug it into the action and expand. And when you did it, you got this action right there. And we see that there is a quadratic term for the first component of delta x, and that indicates that the first component has a mass. And that's very intuitive because that's just fluctuations in the direction of the vacuum, which is precisely the fluctuations where we do get some curvature. Right? So if you are in the direction of the vacuum, that's exactly the fluctuations which cost energy to move. Right? So these are the massive fluctuations. Whereas the perpendicular ones should cost no energy, because exciting a fluctuation in that direction is just going to another vacuum which is equally good. So those fluctuations should cost no energy, and indeed they are massless particles. And these massless particles, so this n minus 1 massless particles, are called Goldstone bosons. Okay, notice that I could have in general, whenever I have a field theory, the quadratic term, I have the kinetic term, and then the phi square term is where I read off the mass of my fields. So in this case, it was very straightforward because it was diagonalized. So I had one field of mass m tilde square and one field of mass 0, and n minus 1 fields of mass 0. But more generally, what you expect to get is something like this. If you have a quadratic action, you have two fields and you have some matrix. Let's call it a mass matrix. And if when you diagonalize the mass matrix, you read off the various masses of your fields. But here the matrix is diagonalized for us. The matrix was diagonal to start with. It was m squared, 0, 0, 0, 0, 0. If it was not diagonal, we would rotate the fields to make it diagonal, such that we would identify properly what are the various modes with its various masses. Right? You agree? So someone could, yeah, that's right. Okay. And then there were two interactions when we expand this potential. We are expanding the potential. We got a cubic term and a quadratic term. And I just want to point out that if you want, but you don't need to, but if you want, you could use Feynman graphs and represent graphically these vertices like I drew there. So I chose to say that when I have a propagator of a field 1 with a field 1, which is a massive propagator, I draw it as a dashed line. And when I have a propagator with a solid line, it means that it's a delta x with j from 2 to n. And you see that the vertex A contains always particle 1, but coupling to all the components. So when I write all the components as component 1 plus the other ones, I generate two vertices, which I drew there. Whereas B has the quartic term with all possibilities, so it can be heavy, heavy light, or light light. And those are the four graphs I drew there. And you see that I drew the vertex like so. You look at the first vertex in B to indicate how the indices are connected. Okay? Just to indicate that color is preserved along those lines. And again, that's just graphical notation. Yes?
So over here, we're treating x as the field, and then it seems like we switched to treating delta x as the...
Yeah, because we just expanded around the solution. So the integral over x, it was just a translation, became integral over delta x. Right? So that's an important point, and let me emphasize that there's no approximation here. Right? That here, my z, right, it was equal to the integral over the dxn of exponential of minus my action of xn. And this is equal, no approximation, to integral over d delta xn, right, times exponential of minus my action at x classical plus delta xn, because this is just a translation. It's like for each variable, I just translate the variable. And since I'm integrating from minus to plus infinity, it doesn't matter. Right? So there is it's an equality. But the second sign is more useful, because then I know that if this is a minimum, right, when I expand around it, these fluctuations are going to be small, so it's better to use the variables delta x. But then, are these fluctuations really small? Well, for example, we could compute the expectation value of x1, and now because a cubic term was generated, when I bring down the cubic vertex, I have 4 delta x's in total, and I can draw the Feynman graphs and start drawing, for example, this, where this represents a contraction of type 1 with type 1, and this represents a 2-point function of type j with type j, where j would be 2 up to n. And I chose this one because this is the one that is potentially dangerous, because it involves the flow of a massless field. And indeed, it is dangerous sometimes, because this propagator, It is just 1 over k squared at small k. If I'm in the lattice, or it's exactly 1 over k squared if I'm already in the continuum. And this is divergent if d is equal to 2. So I started under the assumption that symmetry was broken and that I was at a vacuum plus small fluctuation. And then I saw that that assumption is not good because the small fluctuation is not small after all. Right? So fluctuations are not small, so there is no spontaneous symmetry breaking in d dimensions for continuous symmetry. And more generally, we had argued, based on just entropy considerations, that was what we expected. We were discussing this entropy, who wins against who, and we saw that if the symmetries are discrete, in d equals 1, entropy always wins. And if symmetries are continuous, both in d equals 1 and in d equals 2, entropy always wins. Whereas if you are in higher dimensions, it's possible to have, as we see in this example, but more generally it's true that it's possible that both could compete. Okay. Now, let me just, so on this statement that there is no spontaneous symmetry breaking here, it's also called Mermin-Wigner theorem. Okay. Notice that a consequence of this, a statement like this, of this being finite and this divergence, is the counterpart of the following. It's exactly the same as the following statement. It's the statement that in position space, x at position n and at position n plus m, it behaves, if m is large, as 1 over the distance, m, to the power d minus 2, if d is bigger than 2, and therefore it goes to 0 at large distances, meaning that if you have a massless field, fluctuations decay at large distances. And if you were to compute the Fourier transform in d equals 2, it would diverge instead logarithmically with distance at d equals 2, so it would blow up at large distances, indicating that these fields would be pathological. Their fluctuations are growing and growing and growing at large distances. Okay? And this will tell me that Goldstone modes in d equals 2 would be pathological, hence they don't exist. So to make it into a theorem, let's prove the following theorem, and then we will thermalize a quantum table. Okay. So I'm promising this thermalization forever. I feel like these TV shows that we know the fight is going to happen, like Game of Thrones, and then okay, maybe it's in the next one, maybe in the next one. But today we will thermalize the table. Okay. For sure. Very good. So the theorem we want to prove is something like this. So we want to say that so basically the way we would convert this into a theorem is saying that if I have some symmetry, and this symmetry is broken, right? It implies the existence of massless modes. In other words, that is, that the matrix Mij square has 0 eigenvalues. Right? That's the invariant way of saying that there will be a matrix M that has 0 eigenvalues. But then, in And this will be general always. We will prove this now. That's what we are going to do next. But then in d equals 2, we would reach a contradiction, because then we would say that symmetry broken would generate these Goldstone modes. But the Goldstone modes, but they are pathological, they cannot exist, they are not good. And that implies that there is no symmetry break. And this is what's called the Mermin-Wagner theorem. So this would be, as I said there, this Mermin-Wagner. Whereas this one here, that we are going to prove next, this one is also a theorem, and it's called Goldstone theorem. Okay? So Goldstone theorem as a cute proof, so let's do it. Let's just prove this theorem. And that closes the loop of ideas that we started last time. So to set the ground, let's remember here. So we had, so let's clean up a little bit our case before we do the general case. So we have a field X in the vector representation of On, right? More generally, let's see here what we were going to do. We could say that I have some field phi j, where j could take values 1 up to m in some, can you read? I can barely see. In some representation of some continuous group G. Right? So that's what we have a particular case, and here we would have the more general case. And then here what did we do? We said that x is equal to some classical x, and this classical x was pointing in some direction. And then there were n minus 1 components here, plus some fluctuations, delta x. Okay. And you see that here, the full vector transformed under On, but now the remaining, which is equal to 1 and then d of On minus 1, these are the symmetries that preserve the vacuum. Before I could rotate any vector, now I can rotate these n minus 1 zeros. So basically I have, after I fix a vector, I have the remaining orthogonal directions, right? So I have some vector I fixed, and now I can rotate in the perpendicular planes, right? So the symmetry here was broken from On to On minus 1. Now, how many symmetry generators do I have in On? How many transformations I have? So how many rotation generators are there in On?
Metric, so n into n minus 1.
Good. So here we have n minus 1 over 2 symmetries. Let's just check if it works for n equals 3. So when n equals to 3, we have 3 rotations around 3 rotations in the 3 possible planes of rotation, x, y, x, z, y, z. And here, therefore, we just replace n by n minus 1, n minus 1, n minus 2 over 2 symmetries. And so the difference if you compute this difference of how many symmetries you have, how many symmetries you lost, it's equal to n minus 1. So again, what are these symmetries? These are, here, are the symmetries that preserve the vacuum. And these were the original symmetries. So these ones are how many generators move the vacuum out of the original symmetries. Right? So out of the original symmetries, some transformations move that vector x classical and some leave it invariant. Right? How many transformations move? N minus 1 in our case. There were n minus 1 perpendicular directions where the vector moved. Right? Now, if you move the vacuum, what do? You go from a vacuum to another vacuum. Right? You move the vacuum, but it was a symmetry. So by definition, it will be mapped to another vacuum. So therefore, these n minus 1 directions should cost no energy. So this will be, and it was, but we will see it, that should be indeed equal. This was the number of Goldstone bosons. Right? So they move the vacuum into another vacuum, hence costs no energy, hence costing no energy. And therefore, they were the Goldstone bosons. So this was the basic idea that we had before. That's how we understand it. Now let's try to understand this. So the claim is that this difference, what we want to prove is that this difference, which is the number of generators that don't leave the vacuum invariant, are the number of particles that have 0 eigenvalue for our mass matrix. Okay, so let's try then to prove this general theorem. So what we are saying is that I have some representation, right? And I'm expanding phi around some classical configuration plus delta phi, put an index j, 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 where what is the fact where this is a minimum. So it obeys the equation that the derivative of my potential with respect to phi j at phi k equal to phi k classical equal to 0. And therefore, once I plug this solution into my potential becomes my classical potential plus the second derivative of the potential, the derivative of v with respect to phi j, derivative with respect to phi k, evaluated at phi classical, just Taylor expansion of my potential, times delta phi j delta phi k. Right? So this object here is exactly what we were calling before my m square jk. That was exactly, I expand the field. Of course, there are plus dot dot dot. This is the quadratic order. I expand it to quadratic order, and we get this plus. But we are interested in going to quadratic order to see the properties of my fields. Okay. So now consider a symmetry transformation of our continuous group G that sends phi j an infinitesimal transformation that sends phi j into phi j plus alpha some infinitesimal parameter times some symmetry transformation that would depend in general on the fields. Okay, so for example, in our rotation, this would be just alpha, some omega jk phi k for an infinitesimal rotation, but in general it could be some symmetry transformation where I'm choosing these transformations which are not symmetries of the vacuum, so the ones that move the vacuum. Okay. Then, because it's a symmetry, we have the following property. So for constant configurations, the action is invariant under a symmetry, but the kinetic term is irrelevant because they are constant. So constant means that kinetic term can be ignored. And invariance under a symmetry would imply that my potential at this field phi j plus this infinitesimal parameter alpha delta phi j is equal to my potential at phi j, that's the definition of a symmetry, where this is basically, which implies that derivative of the potential with respect to phi j times delta j of phi equal to 0. Right, this is true. And now we just take a derivative with respect to phi k of this equation, and after taking the derivative, set phi to be equal to the classical phi. Okay, and let's see what happens. Okay, let's do it. So the derivative can act on the transformation. For example, here it would act and give just omega, or it can act on the potential. So there are two terms. One is derivative with respect to delta j, derivative of delta j with respect to phi k at phi classical times the derivative of v with respect to phi j at phi classical. That's the first term. And the second term is plus delta j at phi classical times second derivative of v with respect to phi j with respect to phi k at phi classical equal to 0. So now at phi classical, this is equal to 0 by definition, right? This is equal to 0 by definition of phi classical. Phi classical is a minimum, so the derivative of the potential is equal to 0. This term is basically, no, it's exactly, actually, our mass matrix m square ij, right? So what is this equation tell us? This equation tells us that these guys are eigenvectors of my mass matrix with eigenvalue 0. So it tells me that there are how many of those? Well, as many as symmetries which are not symmetries of phi classical, which was what we wanted to prove. So if you have n minus 1 generators that don't preserve phi classical, you will get n minus 1 eigenvectors which have mass 0. Okay? Is it clear? Notice that it's crucial that there are not symmetry generators, otherwise this delta is 0 by definition. Being a symmetry means that the transformation of my field is 0. Okay? So that's the theorem. So this is Goldstone's theorem. That for each symmetry that is broken, for each symmetry that is not a symmetry of phi, there is a 0 eigenvalue. So again, the idea is very intuitive, right? So I started with some symmetry, and you chose one vacuum. That vacuum is pointing in some direction, right? Now, you have some symmetry transformations that move that vacuum to another position. But the theory was symmetric under some group. So that new position is also a vacuum, right? But it costs no energy to move. So how many generators you have that act on your vacuum should be how many modes that cost no energy, which are massless modes you have. So these are modes that don't cost anything to excite. They have 0 mass. So it's totally intuitive, and this is a simple way of proving it, that if you think a little bit about my words, this is just making my words into formulas. It's literally just that. Okay, so we have these notions of Goldstone modes, Goldstone theorem, Mermin theorem, and I just want to make one more comment before now we move to thermalization, which is that here, what we saw there at the very top is what are called infrared divergences. So these are divergences related to long distances. It was the axis becoming very large or the momenta becoming very small. We also saw some examples of ultraviolet divergences before, when we said that if I go to long distances naively and ignore that I'm on the lattice, some Feynman graphs were diverging. And it's very important that it's totally different. One is short distance physics, the other is long distance physics. Short distance physics typically tell me that I am ignorant. I don't know the lattice details, but once I figure out the lattice details, everything should be finite. If I'm on a lattice, everything should be finite. But the very important lesson is that infrared divergences are very different. They are physical. Once you see an infrared divergence, it means you did not understand something. You start getting infrared divergences, you should wake up and say, what am I doing? For example, here, it would be the example. I'm expanding around, I'm assuming symmetry was broken. And then I start getting infinities. It's a warning. It's like, stop. Symmetry is not broken. Okay? And that's a general lesson. So infrared divergences, they always signal something physical, important to understand because they are related to large volumes. So it's not details of something we don't understand about the UV. UV divergences, they are often less mysterious, even though people sometimes make a fuss out of them. But the infrared ones are the most physical ones, at least from this point of view. Okay, so
Sorry, could you bring the bottom board, please?
Yes, hold it. Okay, I need an adapter, Lauren. I just realized I don't have. Sorry.
You have your charger?
I have my charger, but I forgot the adapter to connect to the projector. And I should raise this one. Yeah. So.
Comment what still holds when these symmetries are local instead of global?
That's a very interesting subject. So if the symmetries are global rather than local, there is a Higgs phenomenon and so on that is very interesting, but I don't want to discuss it now. That will take me on a different route. I could give a lecture on Goldstone mechanism if you want, on Higgs mechanism. But now, no, it takes me out of the logic of the lecture. Okay. I think we can, I don't need to write anything in the blackboard because it's pretty clear what we are going to do. So, or actually, I will write just one thing. So, thank you, Lauren. So what I would like to do today is very simple, is to study the analog of thermalization for a quantum table. And there were some references in the wiki. Did you have time to have a look at those references? No. But what they did is the following. They asked the following question. So what happens if I start with a pure state and evolve it in time? So it's the analog of punching our table. So I start with some state and I evolve it in time. And the idea is what they propose as the setup, this is from the reference that is in the wiki, is the following. Start with a lattice that has some door there, and you put a bunch of hardcore bosons, which are bosons that in each side of the lattice the boson can be empty or it can be there. And you put them all on this corner of the lattice, and then you open the door and let them move and thermalize. So we will start in the ground state of the bottom. The door is closed and we start in the ground state. So what's my state? Is the ground state of the bottom. So it's not any ensemble. It's not canonical, it's not microcanonical, it's just one eigenstate. It's in the ground state of the bottom. Then I open the door. Now, for the full Hamiltonian, what was before an eigenstate is not an eigenstate. It's a linear combination of all eigenstates. So now the state evolves, right? So now the state evolves. So if I decompose in eigenstates of the full Hamiltonian, each eigenstate is now just evolving with a phase, e to the minus the energy times time, right? And the question is, what happens when I evolve this Hamiltonian? And the claim is that we should observe some plots like this. That's from their paper, where we start relaxing dynamically. We start doing the exact diagonalization of the Hamiltonian and we evolve our states. Here is some quantity that we compute. I'll define this quantity soon, but it's related to the occupation number. How many particles are there that have no momentum in the x direction? And then you see that you compare the diagonalization that you compare with the microcanonical ensemble. This diagonal is the average of the blue line, and you see that both are really on top of each other. And they almost agree with the canonical ensemble. And the reason why they are not exactly the same is the system is not that large. It's like it's 21 sites, but it's pretty close. Okay? So this is a very important result. This is called the eigenstate thermalization hypothesis, which is the hypothesis that even if I start with one single state, and then I compute observables in that quantum state, I get the same results that if I had computed this expectation value in some microcanonical ensemble at some fixed energy. That's very important. It's the idea that if I start with some gas in the corner of the room, in some pure state, evolve that state in time, right? So I decompose the corner of the room in states, right? So I start with my wave function of my gas of particles at t equals 0, right? And all particles are in the corner, in a corner of the room, and here it's empty. But of course, I'm in a big room, but this is just a summation of some constants Cn times psi n, where these are the possible eigenvectors, the possible eigenstates, and therefore, right, this evolves to just the sum of Cn e to the minus I ENT times psi n in time. Right? And therefore, when I compute some observable, suppose I compute the average occupation of my particles here. So this could be let's call it capital N, the average occupation of particles here. So the average occupation of particles there at time t would be equal to, I just compute my state at time t, number of particles there, state at time t, and that is equal, once I use my expression there, I have on the one hand sum over n, let's write the diagonal terms, and the diagonal terms will be absolute value of c squared times expectation value of the of some observable, for example, the mean value at position n, plus the off-diagonal term, sum of n not equal to m, of Cn Cm star e to the minus I En minus Em times n capital N M. And so the basic, the question is this equal? Right? So is this equal? That's the question. That's what would make sense physically. That's what our intuition would tell us. That this should be equal to the expectation value of n when I compute this in some, say, microcanonical ensemble, microcanonical, for example, with what energy? With energy equal the energy of this initial configuration. I started some initial configuration. After a long time, I forgot which configuration I started with, but I'm at that energy. So what would be natural is, if I now make some experiment here in the room, I get what I expect from statistical physics, from microcanonical or canonical. They give the same result. Right? So how could that happen? How could this expectation value converge to what we expect? And the hypothesis, and this is purely a property of Hamiltonians, is the statement that these guys better be very small for this to work. They have to be very small. Otherwise, these fluctuations will not die off. Sorry, I forgot T here. So if I want this average to behave like that, our goal is for this quantity to behave like this, around this microcanonical expectation, which is a smooth function of the energy. Okay. And then this needs to happen. These guys need to be very small. That's point 1. And point 2, these guys here, they need to be approximately equal to n, which would be just a function of the energy, this expectation value. And if that's true, that all of them are more or less the same and equal to this, then this sum is 1 by normalization, and then this works. So this works if I have 1 and 2. And 1 and 2 are a very non-trivial property. It's saying that diagonal elements are all smooth functions of energy and more or less all the same, and off-diagonal elements are much smaller. Right? So you diagonalize your Hamiltonian. For example, here the Hamiltonian will be a 20,000 by 20,000 matrix. And the statement is that when you take those eigenvectors and you compute diagonal and off-diagonal expectation values, the off-diagonal should be very small, the diagonal should be all equal to the microcanonical expansion, and this is what's called the eigenstate thermalization hypothesis. Okay? And it's a very natural hypothesis, because otherwise things would not thermalize as we expect, but it's far from proven. It's not something that you can prove very easily. Well, there are people who study. Can I find examples that don't thermalize? And studying time evolution looks something very complicated, right? So you have to start, study time evolution. How do they approach equilibrium? Do they approach equilibrium? How? Are there big fluctuations at some times? Those are complicated questions. But here they are translated into much more straightforward things, which are not about time dependence. It's just about how small are the off-diagonal elements, how smooth are the diagonal elements. So that's why people like it, because it translates some otherwise very vague question into some very sharp questions about smoothness and smallness of expectation of thermodynamic observables in the eigenstates of any Hamiltonian. Okay, so basically we would like, that's our goal, is to study this Hamiltonian where I have a bunch of bosons and they start in the corner, as I said, they start in some corner here, and then they move to the full lattice with this Hamiltonian. And now let's see what this Hamiltonian does. So this B is an annihilation operator and B dagger is a creation operator. So what the sum over neighbors there does is it removes a particle from site J and puts it at the neighboring site I. And the last term, Ni, counts particles at site I and J. Okay? So there is a slight repulsion if particles are nearby. Okay? This is actually basically the table model we considered. It's almost the table model we considered. So if you go to creation and annihilation operator, for the quantum part, the hopping term will be exactly the same because we are coupling the neighbors there. So it's exactly just hopping the terms. But okay, our bosons will not be hardcore and we would have a purely local repulsion. But it is very similar to the quantization of the phonon modes of the table. Okay, so but this is the Hamiltonian, where again the Hilbert space is I just spread bosons here and they move because of this first term and they don't like to be close to each other because of this second term. Okay? Okay, so let's solve this model. Okay, so we have half an hour, it should be okay. Okay, so we start with this lattice. So we'll now solve this. So I want to start with this lattice. So let me decrease so that we can see it in the screen. So I want to start with this lattice which has 5 bisect sides. So I start with some table, I and J, where I goes up to 5 and J goes up to 5. So 5 is equal to 5. Okay, and we make this table. Okay. Now, for example, I can just flatten the first unit. Then I get a list of coordinates. And this is my starting table. And I can just check by list plotting it. I can just list plot it. Okay, and this is a 5 by 5 table. But that's not the table we want, because they tell us to remove some sides. And the idea, why do we want to remove sides? Well, one, because having less sides means the Hilbert space is much smaller. And two, because it becomes more chaotic, because the lattice becomes less regular, so the dynamics are more chaotic, so thermalization is expected to happen better. Okay? So let's remove a few sides. So we start with this start. And we say that I remove some sides. So let's remove side 1, 1. Sorry. Side 2, 2. Side 4, 3. And side 5, 4. And this would be my table where I erased a few links. And we could again list plot. And we see that now we erased a few links, and this is the same table as we had before. Okay? So this is the same table that they have here. Now, I want to write the Hamiltonian, so I want to make a list of all the links between these sites. Okay? So I take my erased sets. So these are the possible coordinates. And I ask, what are all possible pairs of points, subsets, that have size 2? That gives me a possible list of all possible pairs. Okay. And how did I do it? This is hard to read, so I replaced the bottom by F. So this gives me a set of all possible pairs, say 1, 2, 1, 3. Indeed, these are two neighbors. This is this neighbor and this neighbor. No, sorry. Yeah, it's true. Yeah, 1, 2, and 1, 3. This is this link here. But this link is 1, 2, 1, 4. I don't want this link because this link is not a nearest neighbor link. Okay, good. So we say that F of A, B, remove it if they are not neighbors, which means if the norm between A minus B is not equal to 1. Okay? And now I have the link of all nearest neighbors. Okay? Okay, good. So this would be my set of links. Okay, so this would be the set of links. How many links there are in the bottom? Right? If I want the bottom, because I will write the bottom Hamiltonian to first diagonalize the bottom. So okay, so I should create the E raised bottom. So, or just bottom. And bottom would be this erased lattice where I remove the top. So I say that I and j, the top is removed. So remove it if I smaller than j plus 1. Okay. And just to see that it's okay, we list plot, and it's not okay. Why? Sorry. Right? So this is the bottom part of the lattice. And what are the nearest neighbors for the bottom? Well, it is just exactly the same, where I put here bottom, right? And now this gives me all the nearest neighbors in the bottom part. Okay, so we'll want to construct a matrix. So what will we do? We say we start with my links. These are all my nearest neighbors, right? And I want to construct this Hamiltonian. Let's take the Hamiltonian down here, right? So this is the Hamiltonian I want to study. So for each link, I want to have two terms. So let's say that when I have a link, Fij, right? I want to do the following. I want to replace it by minus j, b dagger acting on site I, dot b acting on site j, dot some state, acting on some state. This will be the action of the Hamiltonian on some state. That's the first term. The Hermitian conjugate, I remove the dagger. No, I put dagger with j and I. Right? I just apply dagger to that term, the Hermitian conjugate of that. And then there is plus u, and I count particles at site I and at site j. So what is this? This is b dagger I dot bi. This counts how many particles there are at site I. B dagger j, bj, this counts how many particles there are on site j, dot with state. Okay? So this would be the action of each link. Each link gives me one term in the Hamiltonian. I said j equals 1 and u equals 1/10. So j equals 1, setting one of them to 1 is nothing. That is just saying in which units I measure my time, right? Because that's just Hamiltonian times time is what matters. So setting j equals 1 is nothing. That's just saying that we measure time in 1 over j units. Setting u equal to 1/10 is just so that it's numerical. And we could indeed take different values of u if we wanted. But we are just choosing something. And now each term in my links would give me one term in the Hamiltonian. And what we would do is sum over all terms. And this would be my Hamiltonian, the action of my Hamiltonian on some state. Okay? It's also convenient to have what's the action of the bottom Hamiltonian, and I just replace links by links bottom, and that's it. Okay? And this would be the action of the bottom Hamiltonian on some state. Yes?
When we define these operators in a lattice, how do we translate the commutation relations?
So the question is about the commutation relations. I don't need to, as I'm going to explain. So the reason is I'm putting dots. I'm saying it's b dot b dot state. So Mathematica is never going to swap them. And then I'm going to say how b's act. So that's it. So given a state, I tell you how b acts, then I tell you how b dagger acts. So you will never need to commute them. Okay? But we will need to specify how they act on the state. So that's what we do now. So this was just setting up the problem. Now we need to write it in matrix form. So I want to convert my H, which is something like this. I want to say, okay, now I know how H acts on the states. And I want to write it in matrix form. So for that, I'll create a basis of states. What are a basis of states? So we will put 5 bosons, 5 hardcore bosons that move around, which means that I start from my lattice and I pick 5 sites to be occupied. So I take subsets of that and I apply cat to the elements. Okay? So this would be the various possible states of my Hamiltonian. So the last one, for example, is one where the bosons are at position 4, 5, 5, 1, 5, 2, 5, 3, and 5, 5. Okay? So I could ask, what is the basis when I have just the bottom? I just put here bottom. So this would be the possible states that I have on the bottom. So on the bottom, if I have to put 5 bosons on that small lattice, there are this many possibilities for where to put them. Okay? Just to see, let's see what's the length of basis bottom is 56, and what's the length of basis is 20,000. Okay? So this is okay. So 20,000 is just, the binomial is just saying, how many sites do we have here? So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and we put 5 bosons there. So binomial 21 choose 5 is exactly this. Okay? So it's how many ways there are of putting 5 bosons. Whereas in the bottom, you have less sites. You have just 6, 7, 8. So it's just binomial of 8 choose 5, it's just 56. Okay? So that's indeed the basis that you expect. So we will have to diagonalize a matrix 56 by 56 to find the ground state, to put it there in the bottom. And then we will have to decompose it into these bases, which means diagonalizing a 20,000 by 20,000 Hamiltonian, and then do the exact time evolution. Okay? But let's first write a matrix. So it's easy. So I have to say that I take H, for example, okay, and I say that my state could be the first element of my basis. Okay? And now I have this. I have, for example, the first term is B acting on site 1, 3. So, for example, there, what happens? The first term. Let's look at the first term. It removes the boson at site 1, 3. Okay, fine. There was a boson there, so it's good. And then it puts it at site 1, 2. B dagger at site 1, 2. But there's already a boson there. So B dagger at site 1, 2 will give 0. Right? These are hardcore bosons, we said. So B dagger square will be 0. So, for example, the action on the first term would be 0. Let's see if we find one which is not 0. For example, let's see, one which is not 0. One which is not 0. Do you see? This one. This one removes position 1, 3. and moves it up to position 2, 3, and position 2, 3 is not there. Okay? So it took the boson, removed this, and put 2, 3 instead. So it moves the boson to position 2, 3. Okay? So that's one which is not 0. Okay, so what I want to do is to put a rule that tells me how this acts. So I want to do /dot rule. So what is this rule? The rule is the following. So if I have B of A acting on some cat, okay? So this sometimes it's 0. It's 0 if the particle is not there. This is an annihilation operator. So if the particle is not there, which means that if my cat doesn't have particle A, this should be 0. Otherwise, if particle A is there, remove it. So take C and remove A. Okay? And then sort C so that we bring it to the canonical form. Okay, let's check that this rule did something. So I apply this rule, okay, and you see that, okay, let's not do like this. Let's take one term where we know it should work. For example, let's take this term and apply this rule. And you see what it did. It went and it said, indeed, 1, 3 is there, and it removed 1, 3. Right? Because we acted with the annihilation operator on site 1, 3. Let's suppose we act on something which doesn't have site 1, 3. It gives B dot 0. Because now it killed the state. So another thing we want to add to our rule is that when I have something dot 0, that's 0. Right? So that's good. And now that I add this rule, if I apply it many times, this will give me 0. Okay? Now, I need to teach how does B dagger act there. Okay, so let's do it. So B dagger acting on a cat. Let's put here the rules so that it's easy to see. Again, if the particle is already there, now it's the opposite. If the particle is already there, it's 0. So if it, but if it's not, if it's free of the particle, sorry, this is B dagger. If it's not, put it there. So we can do it like this. We can say sort again, just to bring it to canonical order. So join cat of A with C. So add A, this is adding A. Okay. So let's see that this works. So now I apply rule once, I got this. If I were to apply rule twice here, it would give me 0. Because B dagger, the particle is already there. But if it was the other case, where I put here some other particle, that is, and now I apply the rule twice, and you see it moved particle 3 to particle 1, 2, position 1, 2.
I don't understand why we're considering that B dagger square is 0 if we're working with bosons.
These are hardcore bosons. This is what I said. So these are bosons that cannot be on top of each other.
Oh, okay.
So it's like you have some particles that are marbles and they cannot be on top of each other. So they are bosons in the sense that the B's commute with each other. So if I have B's at 2 different sites, they just commute. But they are hardcore bosons, so B dagger square is 0. So the Hilbert space is just, I just say where they are. But but they are bosons. More questions? If you want, it's like in the Hamiltonian, we think that there is a repulsion which is infinite when they are at the same site. And therefore they just cannot be there. Okay? Okay, good. So now we know how to act on each element of my basis. Right? So what I can do to convert this Hamiltonian into a matrix is I just replace X by any element of my basis. And then I apply the rule. And that's what the action of H is for all the states. Okay? So let me erase this to clean it. This is the rule. This is useful. And this would be the action of H on each of the states. So let's look at it. For example, the first one, the action of H on the first element of the basis. This takes a few seconds to run because it's generating, it's acting on the 20,000 states. So the action on the first one gives this. So that's the action of the Hamiltonian on the first basis element, which is this. Right? So it takes the first basis element and moves the bosons in all possible directions that are empty. Right? Or measures their interaction energy, which is this term here. Okay, so that's, now I have a table of action. Now I have a list of actions. And now I can just ask to convert it into a matrix. I look at that action. And this is just write it, give me the object as a matrix. Right? So this is just H as a matrix. So we can just plot it. So this is the Hamiltonian we want to diagonalize. So it's a 20,000 by 20,000 matrix, which is mostly diagonal. It's a very sparse object, and it has some off-diagonal elements. Okay, so let's just check what we are doing to see that it's good. So let's act with a Hamiltonian with this matrix. Now it's a matrix on a vector which is 1 in the first element and 0 in the rest. Okay, so let's do that. Let's say table, if I equal to 1, give me 1, otherwise 0, where I runs up to this value. Right? So that's our vector. Right? And let's, for example, act with the Hamiltonian on that vector. Okay? So that gives me a 20,000 by 20,000 vector. You see? This gives me a vector. This is my basis. So if I dot this product with my basis, I get this, which was the action of the Hamiltonian on the first basis state. Okay? So it is just I act on the first state, I get a vector. If I convert it to the language of my basis, I get the same as the action of the Hamiltonian. Okay? So is it clear? So when I have my basis, each element in my basis, so the element number 10, which is this, corresponds to the vector 0, 0, 0, 0, 0, 1 at position 10, 0, 0, 0, 0, 0, 0, 0. Right? And the Hilbert space has dimension 20,000, so matrices have size 20,000. Okay, so that's the matrix we want to diagonalize. Now we are in business. Now now it is just about diagonalizing this matrix. But we said that we start with the bottom. So what we actually also want is to diagonalize the bottom matrix. So we just say H, action of H on the bottom. That is just I act with H on the bottom on the basis of the bottom. And then H matrix for the bottom would be just this over the basis of the bottom. So that's a 56 by 56 matrix. And you see it's a much smaller matrix. And that would be the matrix we will be diagonalizing to start with the ground state. Okay. So that's what we do now. So that we do diagonalization of bottom corner. That is starting point. Okay, so we start with H, matrix bottom, our 56 by 56 matrix. We can explicitly write it as a matrix. Here it is. You see? That's the matrix. Let me do something smart, which is to make U equal 0.1 rather than 1/10, because then it's numerical, and because then it's it's numerical, and my matrix will be a numerical matrix. Because now when I make eigensystem to diagonalize it, she doesn't try to solve it analytically, which is of course impossible. Okay, and this would be my eigensystem, the diagonalization of the bottom part. And the first element of eigensystem are the eigenvalues. So, okay, so these are the 56 energies of the bottom. Okay? So these are the various energies, and if you see, the second one is the most negative one. That's the ground state. Okay? So this would be the ground state. So if I sort all these energies, okay, and I take the first, this will be my ground state energy E0. So that's the energy where I'm going to start. And what state am I going to start? Well, it was the second one, so it's the second eigenvector. So this is a list of all possible eigenvectors, and it's the second one I want. Okay? So this is the ground state for the bottom. It's this vector here. Now, this here is very ugly, what I did here, because I just put this 2 here, because it was the second one. I should, of course, do this a bit cleaner way. I should say here, find the position of the one which is smallest, call that n, and here I should put an n, such that if I run it in Mathematica 13, which orders things differently, it still works, right? Otherwise, tomorrow I upload Mathematica and maybe this doesn't work, okay? So in my paper I did it properly, but now I want to finish in time, so I'm just putting a 2 here. Okay, good. So what's the vector with which we start? What's the vector with which we start? So we start with this bottom. This is the state we start with. So that's the state we are going to start. Right? I just dotted with basis bottom. But actually, I don't like to make it like this. I like to know how does it look like in my 20,000 by 20,000 element. So I just ask what the coefficient of this state in the basis element J, and J runs over all these 20,000 states. And I make a table. So this is a vector, which now most entries are 0 because no one can be at the top, and some entries are not 0. This is the ones which are at the bottom. Okay? And this would be my vector that I start. Just 1 second. Okay. Okay. So we now decompose vector start as equal to a sum of Cn vector n of the big system, right? And then this evolves to just the time evolution will be just Cn e to the minus I Ent, right? After I decompose the starting point into eigenstates of my Hamilton. Okay? So that's what we do now. We now diagonalize the full lattice. So what do? I take my H matrix. Remember, this is a 20,000 by 20,000. I make it normal to just make it into a normal matrix, and I ask for the eigensystem of this matrix. Okay, and this would be my E system. Okay, and I can ask how long does it take, absolute timing, just to see how long it takes. And here there is a small problem, which is this takes 20 minutes. Okay, so 20 minutes we cannot wait because we only have 10 minutes. Okay, so what we do is we go here and let's change 5 to 4, which means we remove the top row of my lattice, and now I just run everything again. And now all that happened is that the top lattice I removed one line, so you see there is one line at the top removed, So if you go here, for example, this 20,000 is now 4,000. The matrix is now 4,000 by 4,000. This one is still 56 by 56. The diagonalization is similar, and it finished in 10 seconds. Yeah? Okay. So you can run 5. You can, if you have 20 minutes, you can put 5 equal 5 in the top and run. But now we do 5 equal 4. Okay. And now we say, okay, so what are my eigenvectors? My eigenvectors, I take my eigensystem, and it's the second set. This is a list of vectors. Oops, I should not have done this. Bad idea. Okay. This is a huge thing. I don't want to see it. And my eigenvalues are the first element of eigensystem. So these are the 4,000 eigenvalues. Okay. So these are the 4,000 energies. Okay, good. So what about these eigenvectors? So for example, I take the eigenvector number 33. That's one eigenvector. And I take eigenvector number 34. That's another one. What's their dot product? 0. Good. Right? 10 to the minus 17, just numerics. What's their dot product? 33 with 33. Well, depends, but let's hope it's 1. Yeah, it's 1. Mathematica normalizes this properly. Okay? So because they are orthonormal, if I want to decompose my vector start, what should I do? I just dot it with each element of my eigenvectors, and this gives me my the components at time equals 0. So that just means the coefficients C at time 0. Right? These are just the components. So it is, for example, 0.0008 times the eigenstate 2 plus this number times eigenstate 3 plus this number times eigenstate 4 and so on. So those are the constants. And what's now the vector at time t? Well, I will run, what we will do next is run it at various times. So it's better whenever you run at some time, save it. So we say when you run it at time t, you will memorize it. And what is it? So we just take these coefficients, right? And each of them multiply by e to the I t times the eigenvalues. And that's just the time evolution. And that's the time evolution of each constant. So this is C1 e to the IT1, C2 e to the IT2, C3 e to the IT3. And that we dot with the eigenvectors. Right? So notice the notation that here there is no dot. This is just because if I have C1, C2, C3 times exponential of I, this is just syntax of Mathematica, E1, E2, E3 times T, this is this. Okay? It's just because exponential is listable, so it knows to act on the list, it's just list of exponentials, and then product of lists, it just multiplies directly the two elements. Right? So of course this is good, and this would not be good. Right? Okay, so this is my vector at time t. For example, v at time 0 is a vector, it's whatever it is. And v at time 40 is another vector. Okay? So I could put, for example, absolute value and list plot, and this would be the various components of this vector. Okay? And I could do it initially at 4, at 1, okay, at 2, at 50. And you see they are starting to become more spread at type 100, type 10. And what seems to happen here, you see that things at 50 and at 60 they are similar, and at 70 they are similar. When are they changing? At 10 they look different. At 5 they look different. At 4. So that's already a good sign. If we look at the paper that we want to reproduce, you see things thermalize in the beginning. So at 50 it's already thermal. At 25 it's already thermal, more or less. So it's not a surprise. It's around 25 that things should stabilize. So it's good. It seems to be reasonable. So at 20 and 25, things are still changing a little bit, but at 35, not so much, and they don't change much. Okay, yes?
Can I just ask?
Of course.
It seems now like V still has 20,000 components. Why not 4,000?
Yes, good point. Because I was not showing you V, I was showing you something else. Sorry, you are totally right. It was just wrong. I can explain why it was wrong, but so let's redo it now properly. So it has 4,000 components. Good point. The point is that I'm saving the value. And in another notebook, I did it with a 5 by 5. So she was recalling the previous values I had saved in another notebook. So it was not showing the correct values. But I don't want to call it V because later I'll show you the results with 5 by 5 so that you see. Okay? But this is with W, how you would get. So again, it starts different, right? At 1/10, it's like this. Here, it makes sense to do plot range all. So all the values are picked, and then they start to distribute, and they distribute more and more and more, and eventually the table will thermalize, and all vectors will be equally occupied. All positions will be equally occupied. Now, they tell us to, okay, so now we compute an observable by time evolution. So let's compute 1 over L square or 1 over Lx, Ly, if there are two different lengths, like in our example now. And we do exponential of minus I kx nx minus I ky ny times times b dagger at position nx ny dot b at position nx ny. So, and the quantity they propose to study is this sum over kx and ky. Okay? And this would be, let me just see if I did it correctly. No. The sum over nx and ny. This would be the Fourier transform of b dagger, which is just the occupation number. So this would be the occupation number at position n, and this is the Fourier transform. So it's the occupation number of mode k.
You've got xn instead of nx in the exponential.
I will not run it. It's just for explaining what I'm doing. And furthermore, so this is what they would call n of kx, ky. So this is the Fourier the n at kx, ky. And, sorry, 1 second. Sorry, just a second. Okay. Oof. Totally confused. And then what they are plotting in this quantity is n with kx equals 0. Okay? Just to simplify, so they put this quantity n with nx equals 0. With kx equals 0. So should be 0 here, and I am confused by something. Give me a second. let's remember exactly what the observable is. Okay, but let me do the following. Let me we'll check what observable they compute, but it really is, for the purpose of what I'm doing, I can, let me just go here and copy paste it from here. So we'll see in the paper that this is, it's some average of some occupation number, but this is the goal we have, which is this. So you see that this is, it is just occupation at site 2, at site 1, 2, occupation at, it's some linear combination of occupation b dagger dot b, where we sum over the position. So it's some occupation in Fourier space. Okay, we Fourier transform, and we do some sum over positions and vectors. So that definition there is really, right now it fall out of the blue, but if you see in the paper the definition, it is just something natural to measure how many states there are in some momenta. And that's because if you were to do some scattering experiment with light, sending light in some wavelength, that's the kind of thing that we would more naturally measure. So instead of measuring occupation at one site, you just measure occupation in some wavelength. Okay? So it's just some Fourier transform. It's just some object that we want to study. Okay, so what would we do now to check what we want to do? Let's do it quickly now. So we say that, so this is the object we want to study. So action goal would be the same as before. We take goal, we replace state by x, we apply the rules, and we do it for any elements of the basis. And then my goal observable as a matrix, it is just the coefficient array of action goal in terms of basis. And I guess it's element number 2, we'll see. Yeah, it's 4000 by 4000, it's good. And then what should we do? Now we do what I wrote there in the background. We take our bra, so it is the conjugate of my vector v at time t. We dot it with the matrix, we dot it with vector at time t. That's just the expectation value, right? And we do it as a table of time and then this vector for many times, says time from 0 to 100 in steps of 1/2. Okay, and we can monitor the time. And this would be our table. Yes, good point. I should have W instead of V. Good. So it's now computing this table. Right? So that's our experiment. So we take our experiment. It's just chop this table, and I list plot it. Okay. And that's my experiment. Yeah. Okay. So this is our thermalization, where things are going around this average. Okay. And this is what we'll call our experiment. Okay. And now we compare with what we expect if we did the computation by microcanonical ensemble. So we have our energy, E0, right? And what we would do, we take our eigenvalues, there are 4000 of them, right? And we are going to sum over states that have this ground state energy. How many states are there with this energy here? With exactly this energy? 0. This was a state of the Hamiltonian when I did not have this door. Now I open this door, I get a different spectra. There is no state with this energy. So what I should do is take a window. So I should make a delta, say. And now which delta? Let's pick 1/10. but you could pick something else. And now let's ask which eigenvalues, which ones are between E0 minus this delta and E0 plus this delta. Okay, so these are the eigenvalues. And we can flatten. So it's the eigenvalue number 355, 358, blah, 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 up to 410. Those eigenvalues, these ones, with these positions, they have energies at close to the ground state energy. So what do? I take those eigenvectors where J goes over these positions. So these are the positions of the states, and I make a table of this, and this would be the vectors in the microcanonical ensemble. Those are the ones that have energy. Right? So this is, there are 26 vectors, each of them with size 4,000. This is how many states there are. And what's our prediction for the microcanonical ensemble? It's 1 over those states, how many states there are, right? And we sum over all states which are in the microcanonical ensemble. Right? And what do? Let's call it psi. We sum over all such states, and we do conjugate psi dot our matrix we want to study dot psi. We just compute psi on the states that have that energy, right? And that's the microcanonical expectation. So the theory that we expect is the plot of this from t from 0 to 100. So this is what we expect for theory. And finally, we can put comparison. And we ask to show theory and experiment. Okay. And this would be how we would see that the time evolution of the state approaches the. We start with a pure state and we quantum evolved. Or, in the second case, we just computed all energies around this energy and we made an average. And you see that it converges pretty much to the same thing. So this is ETH working. With a smile. Yeah. So let me just maybe show you here that this is a notebook where I had done 5 equals 5. So here 5 is equal to 5. I'll upload this, we'll upload this notebook. So 5 was 4, but then I said 5 is 5. Okay? So when 5 is 5, the matrix is 20,000 by 20,000. And I also did here, you see that the microcanonical ensemble, I could have chosen, instead of 1/10, 1 over 20, 1 over 30, 1 over 40. It's a bit arbitrary, right? Which window do you choose? Depending on which window you choose, you see you can have, sometimes you have many states. Remember, this is this 20,000 by 20,000, so there are many more states. So with 1/10, there are all those positions there. And then with 1 over 40, there are this, which is roughly the same kind of number we had in our case with 1 over 10, right? So we could try to do microcanonical with all these possible small windows, delta 1, delta 2, delta 3, and they give different results. And here would be, you see, the various results here, and we show here the thermalization, how it would compare with experiment. With a bigger length, it works better. Actually, ours looks like it works better, but look like it's very unfair because of the plot range, right? So it's because here she started from 0, then everything looks squeezed. So it looks much better, but it's just because if I put the same plot range here, this would look spectacular, right? Now it looks it looks much better. So this is If you are a marketing professional, that's how you do it. Okay. So, okay. Or you can go to the previous one and make it honest, and you would see that this one is much better indeed. So microcanonical depends a bit on the width that you do, of course, on what resolution do you call your microcanonical ensemble. The values are all more or less similar though, and the exact time evolution oscillates around those values. So there are two things for your homework that you will be given today. One is to take the table problem we did and study what happens when this n. So for the tutorial, the first question is to study what happens when n goes to infinity. And in particular, you should see that when n goes to infinity, the Feynman graphs simplify because only a simple class of graphs survives. So we can actually sum all graphs, which is pretty awesome. And that's some analytic work. And the question 2 is the quantum thermalization, which is a bit like the first homework. I think it's very instructive to just take this notebook and play a little bit with it. And what does it mean to play a little bit with it? It could be something like this, for example. It could be plot other observables. So there is this observable, which is the one they propose in the paper that you can see. But you could start with other observables, like expectation value at some sites, and you could again compute them using various ensembles. You could start with other states rather than starting with the ground state in the bottom. You could start with the most excited state. Does it also work? I think so. You could compare with canonical ensemble. We don't need microcanonical. We could compute the canonical. It's just e to the minus beta times the energy. We know all the 20,000 energies, so we can just sum them, right? And we can compute what happens in canonical ensemble and see that, like in the paper, it should be a line that is not as good as those, but also close. We could study more about this delta dependence and understand this arbitrariness about which window to choose, what's the best one, what happens if I change the windows, and I studied the dependence on the windows. I took some repulsion between the particles, but that was because it was the one they did in the paper, but I don't know what would happen. We could try to do time averages. Instead of seeing all these fluctuations, we could coarse grain a little bit and see what happens as I coarse grain in time and I start seeing things converge. So it's more or less open-ended, and I think we will type it down a little bit better, but that will be the second part of the homework. It is just to play with small deformations of the node. Okay, very good. So I think that's it for today. Thank you.